questions. Is okay?
Yeah, perfect, perfect.
Okay, so then, yeah.
Yes,
So
thank you.
yeah, okay, just I will introduce you. So the first member of this session is Ian Guten-Noir.
Guten Noir. Guten Noir.
Guten-Noir, okay, sorry. Cosmological consequences of supercooled confined phase transitions. Okay, thank you. Please start.
Thank you very much for giving me the opportunity to introduce my work. So first, I will introduce myself. So I am from France, but I did my PhD in Hamburg, in DESY, in Germany. And I'm currently moving to Tel Aviv University. Actually, I moved here 2 days ago, and I'm currently in quarantine. I should be able to leave my apartment in a few days. And here it's a work in collaboration with Yazan Baldes, Filippo Sala, and Géraldine Servan, done mainly in DESY. So you all know the super uncool confinement, which started early 2020 with a virus outbreak, underwent a propagation stage, and ended with a vaccination stage, which is actually still going on. But today, I would like to talk about super cool confinement. So super cool confinement, in contrast to super uncool confinement, started with a vacuum outbreak. So if you want, it's a phase transition where which is super cool. So it started with vacuum outbreak, then underwent an inflation stage, and ended with nucleation. So super cool confinement is so first it's a confinement. So it's a phase transition like QCD, where the theory becomes strongly coupled. So this happens when the bubble of new phase, of confining phase, nucleates at the late stage. But here you have a stage of supercooling, because if you want, so the phase transition is supercool, which means that there is a hierarchy between the nucleation temperature and the confining scale. And in between, when the temperature of the universe is in between, the universe is dominated by the vacuum energy of the phase transition. And today we will explore the consequences of such confining supercool phase transition mainly on dark matter. So what would be dark matter in that picture? So here we have a confining sector. Let's say dark matter is a mesons, like form of a quark and antiquark of that sector. And let's follow the evolution of the quark-antiquark through all those stages. So when the universe becomes vacuum dominated, it's gonna inflate. So the quark-antiquark are gonna be put very far away from each other. Their density is gonna be diluted. But then the strong sector confines, and you should form some hadrons. And you expect that the consequences of this supercooling stage is a dilation of the dark matter abundance by the ratio of temperature to the cube, just a volumic dilation, right? But actually, this is not what should happen, because the quark and antiquark are very far away from each other. So when the strong sector confines around the nucleation stage, you should form a string, and this string has a huge energy. So let's be more precise. So here is what happens when the bubble nucleates. So this dashed line is the bubble wall. On the left is a deconfined phase outside the bubble, and on the right is a confined phase inside the bubble. And here is a quark and antiquark, which we are in the bubble wall frame. So in the bubble wall frame, they are like moving towards the inside of the bubble. And here on the top is what we expect for the bubble wall profile. So the confining scale is 0, then it oscillates a bit, and then it takes its true value. And what happens now dynamically, right? So quark-antiquark arrives. So first they have a very shallow string which links them, but it's very shallow because the confining scale is very close to 0. But once the quark-antiquark enters the confining phase, they form a string of huge energy. Because why huge energy? Because as you know, the potential for a strong force grows linearly. But here, the distance, as I told you before, between the quark-antiquark is very large because of the dilution stage, because of the supercooling. So then the string energy is huge compared to the typical confining scale. It is enhanced by the ratio F over T nuke, the ratio of temperatures. It is enhanced by the supercooling stage. So this configuration here that we have on screen costs too much energy. Instead, the flux tube wants to minimize its energy. So it wants to stay outside, because outside the confining scale is close to zero. So the flux tube has a vanishing energy. But then effectively, what happens is that effectively each quark interacts. It is as if each quark interacts with the wall, mediated by a flux tube, mediated by a string. And once the flux tube length becomes above F-1, you should expect the string to fragment. This is analog to string fragmentation in QCD. And then you should expect hadronization, so formation of more hadrons. In addition, if you think about it, if you want to conserve color conservation, so here you have one color charge that has entered, then you form hadrons that are color singlet. And this quark will form the initial quark will form a hadrons with one of the quark of the fragmentations. But you need to, where is that initial color charge that has entered? You need to eject it. And this is analog to Hawking evaporation, but it's just a metaphor, just for the fun. So what are the impact on the dark matter abundance of that? So first, you see that because of hadronization, but also quark ejection, you have more, mainly because of hadronization, you have more hadrons per initial quark pair. So instead of the naive dark matter abundance coming from dilution, you have an enhancement which is logarithmic. Why logarithmic? Because we have used Pitya to know how many hadrons we produce per string. And we have found that we have just fitted, and it is something close to a logarithm function, which depends on the Lorentz factor of the wall. You see, the gamma, the faster is the bubble wall, the more energetic is the string breaking, and the more hadrons you produce. And this further enhances the dark matter abundance, because we said dark matter is one of those hadrons. But there is a second consequence. Is what we call the cosmological catapult, because if you want, the string is attached to the wall, but the wall is moving with respect to the plasma frame, with respect to the CMB frame, if you want, or with respect to the frame of the center of the bubble. So the wall is moving, but the string is attached to that wall. And once the string breaks, the hadrons that are produced in the center of mass frame of the string. But the center of mass frame of the string follows the wall. So if you want, the hadrons, once they are produced, they follow the wall. So you can view the metaphor as if the string acts as a catapult, the string attached to the wall acts as a catapult for the hadrons coming from the fragmentation of that string. And then the hadrons, they are propelled in the universe with a huge momentum. Here in range are the hadrons that are just produced from the string fragmentations. And here is their energy or momentum in the plasma frame. And this is enhanced by the gamma factor of the wall. And then what happens to those hadrons which have a huge momentum in the universe? They will scatter with the bath, with the plasma, for instance, which are typical energy F being the confining scale. And if you compute the S of the scattering, Mandelstam variable, you will find that it is much larger than the confining scale, square. So you will probe the internal structure of the hadrons. So this will produce deep inelastic scattering. So scattering will be deep inelastic, which means that you will produce a shower of additional hadrons in a range here. But again, these hadrons have still a huge momentum, a bit smaller than the initial one, but still it has a huge momentum. So then you will have a cascade of deep inelastic scattering until the momentum of the daughter particles is not enough to produce further deep inelastic scattering. And what happens is that all the kinetic energy of the hadrons is converted into mass energy. So you will further enhance the number of hadrons, but by how many? By a gamma factor, because gamma factor is the initial kinetic energy of your hadrons. Per each hadrons, you will produce gamma more hadrons. So you see, for supercooled phase transition, gamma can be 10 to the 10, so you can produce 10 to the 10 hadrons starting with one initial hadrons from string fermentation, which has been catapulted in the universe. You can produce 10 to the 10 more hadrons. Okay, and now let's see the final plot, the money plot for the dark matter abundance. Vertical axis is nucleation temperature, and vertical axis is dark matter mass. So in green is a standard supercool line. So this is when we don't include effects from strongly coupled dynamic. We just include the volume dilution. And you see that already you have thermal dark matter above the unitarity bound. So this is well known that after a supercooled phase transition, you will inject entropy, dilute dark matter, and evade the unitarity bound. But here in this work, we have studied a strongly coupled dynamic, so string fermentation, where the number of dark matter is enhanced by a logarithmic function. So then you will need to dilute more the hadrons, so you need to increase more the amount of supercooling to compensate. And secondly, we have introduced this catapult. We have observed this catapult effect, which drastically change by many orders of magnitude the amount of supercooling that you need to produce the correct dark matter abundance. And you see that this is funny; it's flat in dark matter mass. And this is final horizontal line is a final result. And interestingly, it crosses point where the nucleation temperature is close to QCD. So then if you have you can connect your dark sector to QCD and help the dark sector to nucleate thanks to QCD. QCD can catalyze the phase transition, and this would give you that point and a mass of 1 PeV for dark matter. But you have to be careful because in some parameter space, something happens. Here, the quark are not energetic enough to enter. So gamma T nuke, which is momentum energy in the Wolfram, is smaller than F. The rest energy, there would be rest energy in the bubble. So then the quarks are reflected. So you should expect some snowball effect. We have not yet explored that parameter space. So this is the final result. And in the time that I still have, we'll talk about other consequences. So this was the consequences on dark matter, but other consequences on gravitational waves. So they are well known that for supercooled phase transition, the signal is super huge because the beta over h is super small. It's beta over h is around 10. So you see that the signal is huge, but this is already well known. So we don't produce new results here. Just to show that the dark matter parameter space here, it evades a standard constraint from direct detection and indirect detection. Xenon and S will never probe that region, but gravitational wave will clearly probe that region with a huge signal to use ratio. Even if you have astrophysical background, you should still see it. So this is good news. So this model should be either discovered or probably excluded in the next decade. Next, I will talk about consequences on the bubble wall velocity. So bubble velocity, as you might know, for a bubble of first order phase transition, it is computed as an equilibrium between two pressures. So the bubble wall dynamic evolves according to pressure. First, you have the outward vacuum energy pressure that drive the expansion of the bubble in blue here. So this is given by Cvac F4, F to the fourth. So this is the vacuum energy of the phase transition. And then you have the friction effect from the plasma. And this is equal to number density of incoming particles, which are boosted in the plasma frame, in the Wolfram, times delta P. Delta P is a momentum that each particle entering the new phase exchange with the wall. Momentum exchange with the wall. But the question here that many groups have tried to compute in the last years is what is delta P? For weakly coupled phase transition, there is this so-called Bodecker and Moore result that find at leading order, they find delta m squared T nu square, where delta m is a mass that acquires a particle that enters the phase. And at next to leading order, they found that the pressure grows with gamma. This comes from the possibility for initial quark to radiate a gluons, or initial particle to radiate a vector bosons that acquire a mass in the new phase. But here we are interested in strongly coupled phase transition. And there has been this paper 1 year ago from an American team that have resummed the Bodecker and Moore results at all NLO order. And they have found that this gamma becomes a gamma square. So they have found that the pressure goes a gamma square. But here in our work, published last year, we found using flux tube formalism that we found a gamma. So we find that the NLO result doesn't change. So this is in contradictions, and we will make this debate clearer, this conclusion clearer in the next month, probably, where we also do all order resummation. That's all what I wanted to say for the bubble wall velocity and for the result for the pressure. And I just have 1 minute left, let's say. So I will just finish with that. So here I have discussed new results coming from supercooled confinement. But the question is how much supercooling you need. Do you need a huge supercooling or just a little supercooling to have this effect to appear? So this is the plot that answers the questions. So on horizontal axis is the amount of supercooling, T nu over T critical. And vertical axis is the delta V, the vacuum energy of the phase transition. Delta V over 5 to the 4. The coefficient of the vacuum energy. Sorry for. And on the blue region is the standard phase transition, where the quark, antiquark, the flux tube are not distorted. But here in the khaki region, the green region, actually the strings, the flux tube are distorted. They are distorted, and then you should expect deviation from the standard phase transition. And you see that this start already with very little supercooling, actually. And in the gray regions, so you have quark attached to the wall mediated by a string, but in the gray regions, actually, another quark, a second quark, can come and pick up the endpoint on the wall. And then this will prevent they will stop the interaction of the quark with the wall. So then you should not recover our results, but maybe something occur, something else occur, we don't know. But actually, our results are valid in the khaki region here. So for not too large vacuum energy, but you see that it can occur already with very little supercooling. And here you have to be careful because here the quarks are reflected because they cannot enter the bubble. They are too low energetic to enter the bubble. You should expect new effects. And this has been already explored by some paper. And I will end here, and here is my conclusions. So we have discussed the consequences of supercooled confinement. So you have a stage of dilution, but then you have string fragmentation plus cosmological catapult, followed by deep inelastic scattering that drastically change the dark matter abundance. Then we have said that the friction pressure grows linearly with gamma. We have used the flux tube formalism to compute the friction pressure. And third, we have seen that this should apply already for moderate supercooling, T nu just smaller than Tc. And thank you for your attention. We'll stop here.
Okay, thanks, Ian. So we can have some 1 or 2 questions. Yeah, okay. Takahiro Terada? No, it's just a close. If you have questions, please raise hand up. Yeah, okay. Takahiro Terada,
Actually, I have also a question. Yeah, so you show some fit of PCR simulation, right?
Yes.
To me, it's not a good fit. I mean, to the right of the figure, the deviation becomes larger and larger, and it looks like power law asymptotically. So if you assume it's not logarithmic but some power, then what is the consequence?
So this you're saying that at large energy the fit becomes worse.
Yeah.
I see. So interestingly, this is very funny, but interestingly, the final line here is independent of that function.
Oh.
Because the intuitive idea behind it is that all the kinetic energy is converted into rest mass energy. So the kinetic energy can be, so that function tells you how the kinetic energy tells you how many hadrons share that kinetic energy. But the kinetic energy is the same, whatever the number of hadrons, just that it is distributed into different number of hadrons. At the end, you will know that all the kinetic energy of the initial string, all the initial string energy will be converted into rest mass energy. This is what tells you the flat horizontal yellow line. What tells you the blue line is how many hadrons you will have in the intermediate step between string fermentation and deep integrating.
Okay, so already time is over. So
thank you. Thank you very much.
Thank you very much. Yeah. Yeah. Thank you. Yes, thank the speaker again. Anyway, let's go to the second speaker. Second speaker is Thomas.
Hi.
Krajewski. Hi. Yeah. So are you ready? Can you share?
Yeah, I can share.
Okay.
Okay, I hope you can hear me and see my presentation.
Yep.
So my name is Tomasz Krajewski. I know it's hard to pronounce.
Yeah, thank you.
Today...
Please start. Yeah.
Okay, so can I start now?
Yeah.
Oh, thank you. So today I will present our recent results on of our research on influence of the shape of the potential on stability of cosmological domain walls. So before we start, let me remind you what are topological domain walls. So domain walls are sheet-type topological defects that forms at the boundaries of regions called domains, where a scalar field has different vacuum expectation values. So a potential with at least 2 local minima is necessary for the existence of domain walls. Cosmological domain walls could be produced in the early universe, for example, during spontaneous symmetry break. The dynamics is highly nonlinear and can be studied using lattice numerical simulations. So here we see the model that is usually used in studies of the cosmological domain walls. It is given by this quartic potential, very simple model, with one real scalar field. It has the solution of the equation of the motion that is time independent and planar, I mean independent in 2 spatial directions, in the form of the king. This represents just a single domain, planar domain wall. And in the context of domain walls, this quantity W0 is called a wave of domain wall. So on the left panel, we see this solution that interpolates from one minimum of the potential to the another. And on the right, we see the potential energy density in the direction perpendicular to the surface of the wall. As we can see, the majority of the energy density is stored at the distances of the order of W0 from the center of the domain wall. This motivates this definition of treating W0 as a characteristic scale of the problem, of the width of the domain walls. So such domain walls not exist as a single one, rather it forms networks which can have twofold topologies. So first case, visible on the left panel, is just a finite bubble of the one vacuum that are submerged in the background of the another vacuum. And the second case is an infinite network of infinite domain walls that spreads over the whole universe. So this second case is much more interesting because it corresponds to the networks that can be metastable. However, such metastable networks cause severe problems for the cosmology. It is generally predicted that the effective equation of the state of such a metastable network have a negative barotropic parameter. So first of all, such network would tend to dominate the universe. The average energy density of the network decreases with the expansion of the universe slower than the dust and the radiation. So after some time, it will tend to dominate over the dust and the radiation. Moreover, because this barotropic parameter is negative, it will give the effective negative pressure, which will act as a dark energy, accelerating the expansion of the universe. So some time ago, it was proposed that such a network can be responsible for observed acceleration, current acceleration of the expansion of the universe. However, later measurements of the CMB radiation that was more precise disfavor such large values of the barotropic parameter and favors the value equal to -1. So currently this option is ruled out by the measurements. Moreover, if such domain walls would be present during the recombination, it will distort the isotropy of the CMB radiation. So here comes the so-called Zeldovich bound that means that if such domain walls would be present during the recombination, they had to have energy scale lower than 1 MeV not to distort CMB too much. So the direct motivation for our current work comes from the observation that we made studying Higgs domain walls. We observed that networks of Higgs domain walls were more stable than one could expect from the shape of the potential, which is highly asymmetric. Now, a recent publication, we just tried to understand how the shape of the potential influence the dynamics of the network in more general and more controllable way than we were able to observe during the studies of the Higgs domain walls. So let me stay with this Higgs domain walls for a while. Here we see the sketch plot of the edgy improved effective potential of the standard model. So due to running of the quartic couple of the Higgs, which have a zero around 10 to the 10 GeV, effective potential of the standard model has a local maximum at those scales that separates the electroweak vacuum breaking minimum, which is located at the scales of the order of hundreds of the GeV, from the another one, which for pure standard model appears somewhere at super Planckian field strengths. However, as you can see, this becomes deeper than the electroweak symmetry breaking minimum, quite close to the local maximum. This potential is highly asymmetric with respect to the local maximum. The derivative scales qualitatively as a field strength Q. So it is much steeper on the high field strength side than on the side of the electroweak symmetry breaking minimum. This is visible in the profile of the domain walls too. As you can see here on this plot, this profile is highly asymmetric. So one could expect that this high field strength minimum, this which is not observed today, should be favored by the dynamics of the network. However, it turned out that this is not necessarily the case. In fact, we have found that it is not so hard to find a network that decays into electroweak symmetry breaking vacuum, even if it seems to be highly disfavored by the shape of the potential. In fact, only a small dominance of the electroweak symmetry breaking, basing of the attraction of this minimum, I mean symmetry breaking, electroweak symmetry breaking minimum, is enough for producing a network that decays into the observed vacuum. So this was a surprise for us, and we wanted to understand this effect more deeper. So we started with producing a family of the potentials that in which we can independently control the scale of the asymmetry of the potential around local maximum and the difference of values in the minima. Moreover, we wanted to perform lattice simulations, so we wanted the potential that are given in analytic form and in which we know the position of the extrema exactly. Finally, in order to get the result that would be comparable between simulations, we need to guarantee that all potentials has the same width of domain walls, so the same energy scale for the problem. So we started with setting the potential by its derivative. This is motivated by the fact that this derivative is directly used in lattice simulations. Moreover, we decided to measure the asymmetry around the local maximum using the value of the third derivative at the maximum. Finally, we need to satisfy this last condition, so we need to keep the width of domain walls constant, and this is a hard thing because in order to estimate the width of the domain walls in generic potential, we need to solve the set of integral equations. So getting everything together, we had to numerically solve the set of the equation that are part of the algebraic, and some of them are integral. So the only way to solve such a set is to do this numerically, and here we see the results. So on the left panel we see some representatives of the family that has the vanishing third derivative at the maximum and different various differences of the values in the minima. On the right panel, on the other hand, we have the same difference in the minima. However, we are varying the value of the third derivative at the maximum. In order to list all the parameters that we controlled in our lattice simulations, I need to present how we initialized the field strength. So we used Gaussian probability distribution. This choice is motivated by the stochastic attempt to calculate fluctuations of the light fields during inflation. It predicts that the standard deviation of such a nearly Gaussian distribution should be of the order of the Hubble parameter during inflation. On the other hand, the mean value is nearly untouched by the inflation and need to be predicted by pre-inflationary physics. Moreover, this choice is motivated by central limit theorem. Here we see our results in very compact form. So here we see the decay time of the networks as a function of the difference of the minima on the horizontal axis, and on the vertical axis we see the asymmetry of the potential around the local maximum. These are results from simulations with the vanishing mean value for the initial distribution. So the initial distribution is completely located at the local maximum. And on the left, we see the simulations for the broad initial distributions and narrow one on the right panel. As we can see, the main dependence comes from the difference of the values in the minima, and this asymmetry gives very small effect. Moreover, we are able to confirm that the bias of the initial distribution, that I mean the non-zero mean value of the initial distribution, easily destabilize the network. Here, the blue region corresponds to the simulation that in which we observe the decay of the network to the global minimum, and the red one, the networks that decay into the another minimum. So, as you can see here, even very small bias of the initial distribution easily destabilize the network. And the effect of the shape of the potential is rather small comparing to the effect of the initial distribution. Moreover, as we can do the same analysis for the asymmetry around the local maximum, and it shows that even small effects come from this. So the initial bias gives much stronger effect than the shape of the potential. So if this bias is not fine-tuned to extremely small values, it will determine the fate of the network, and it cannot be compensated by the asymmetry of the potential. In order to deeper understand the metastability of the networks some networks that we simulated, we were searching for so-called scaling regime. So using velocity-dependent one-scale model, which is derived from Nambu-Gotterdsen, one can show that a network of cosmological domain walls has the evolution of the network of the cosmological domain walls has a solution that has a simple scaling if the scale factors has a power law dependence on time. So this solution is called a scaling regime, and it was recognized early in the history of the studies of cosmological domain walls as a tractor of the evolution of the metastable network. So what we done is that we tried to fit this linear dependence to the dependence of the surface area of the walls on the conformal time. And for networks that enter, for some networks that enter the scale that was initialized with mean value equal to 0, we observe such a period of the evolution during the through the scaling regime. Basing on this data, we were able to calculate so-called scaling parameter, which is given here. And we use these values that we computed to estimate the shape of the parameters of the spectrum of the gravitational waves emitted from domain walls. So the amplitude of such a spectrum could be estimated using this expression. And this scaling parameter was computed some time ago for the case of this toy model that I have shown at the beginning of the presentation to be of the order of 0.8. We observed even 10 times smaller values in our lattice simulations. Moreover, the frequency of the peak can be associated to the Hubble radius during the final stage of the decay of the network. So here we see what we predict for a spectra of the gravitational waves emitted from domain walls in generic models. So the peak should be located somewhere in this band. And these dashed lines represent the so-called envelope approximation for the shape of the potential. As you can see, these gravitational waves are too weak or have too high frequency to be detected in current and plan interferometer detectors. So let me sum up. First of all, domain walls in models with asymmetric potentials could be formed in the early universe. This does not spoil the cosmological observables because they tend to decay quite fast, or by the asymmetry of the initial distribution, or by the asymmetry of the potential. Results of our recent simulations suggest that the role of the asymmetry of the potential is not as important as of the initial distribution. So we observe the hierarchy of influence of the factors that we consider. So the most important influence comes from the bias of the initial distribution. Then the non-degeneracy of the minima is much stronger than the details of the shape of the potential. So, two take-home messages. First of all, networks of cosmological domain walls were unstable if formed from biased initial distributions. So, if you want to avoid the problem of cosmological domain walls, you just need to give some bias to the initial distribution, and it is enough. Or on the other hand, if you want to have a network that is metastable, you need to fine-tune this initial distribution to be located around the local maximum. This leads to the conclusion that the observation of gravitational waves from decaying domain walls is highly unlikely because they tend to be unstable. In order to get a strong signal, we need a metastable network that will live very long. And this is generally not the case. So we need to fine-tune the initial distribution and the shape of the potential to get a metastable network. So that's all for today. Thank you for your attention.
Okay, thanks, Thomas. It's the time is almost there, but okay, let's have just one quick questions if you have.
I'm sorry.
Yeah, any questions? If not, then this gravitational wave is observable. Your last slide is.
So the
Yeah.
problem is that you have a very weak signal for the frequencies in which LIGO is sensitive, or you have very high frequencies. So this corresponds to high energy scales like GAT scales, and this to lower scales.
So do you have any other, like for example, this conclusion is model dependent or model independent?
So the only way to avoid this conclusion is to fine-tune the initial distribution, extremely fine-tune initial distribution, because any deviation from location of the initial distribution centrally on the local maximum destabilizes network, and on the same time you need to fine-tune the asymmetry of the potential to be very low value. So
but this but I think in my opinion this is the initial distribution is determined by the, I think it's essentially determined by the property of this for example the phase transition, or just the depth of these two minimal, right? Or they are independent or unrelated?
So not necessarily, because this depends on how you generate this initial distribution. So if from inflation, for example, then inflation will not touch the mean value of the initial distribution. So this comes from some pre-inflationary physics in that case. So it's not obvious to me if you can easily fine-tune this value to zero.
Okay.
Yeah, so this depends not on.
Okay, okay, thanks. But now time is past much, so maybe we have to move the next stop. So please consider. Okay, thank you very much,
Thank
Thomas.
you.
Okay, thank you. Okay, we are a few minutes late, but
hello.
Yeah. Next speaker is Samuel Barroso Valido.
Yep.
So can you share? Did you share the slide? I cannot see your slide.
There is the one sharing the screen, so my Zoom is telling me that I cannot share while the other participant is sharing. Maybe Thomas is sharing the screen.
Thomas, can you?
Yes, I can now share the screen. Okay, can you see the screen?
Hello.
Hello, can you see the screen?
Thomas?
I think that now I am sharing.
Yeah, please try.
Yeah.
Okay, yeah.
Okay,
so Samuel will talk about entanglement entropy.
Exactly.
Yeah, please start.
Okay, thank you very much for the organization to letting me having a coffee before the talk, because it was a mess with the time schedule. And I'm here to talk about entanglement entropy at critical points in the multiverse. This comes from this article we published, that it is special for oscillatories and exotic singularities in the multiverse. But we are going to just say like the most important results we found about the entanglement entropy. The outline is going to be very short. It is like an introduction to canonical quantum gravity, what is third quantization in the sense of canonical quantum gravity, not string third quantization, what is the invariant vacuum that we need for our formalism, and then we are going to find entanglement entropy after all these concepts. Our model is going to be a simple model of a pair of universes that are created from the vacuum, and we will see what are the properties of the entanglement entropy in that scenario. So we can drop some important mathematical properties and physical properties of the system, just looking at the entanglement entropy, and then some conclusions. Canonical quantum gravity, if some of you are not aware of this is an old stuff. This is something from the 70s, so from the 60s, sorry, and it comes from after a article published by Dirac and the ADM formalism. This simply, the formalism says that you can, in general relativity, generalize general relativity, changing the canonical variables of the theory. Instead of having a metric, a 4 metric, you have a 3 metric and some function, some lapse function. If you foliate the space-time like this, then you can see that the dynamics of the universe is only given by this function that give you the steps in time of each hypersurface of the spacetime, and the 3 metric. The 3 metric behaves like the dynamical variable of the system, from where you can get the energy of the system. So you can define as the new canonical variables the momentum of this new 3 metric. And you can quantize a la Dirac also the scalar fields or anything you have in your system. The point is that the master equation is the Wheeler-DeWitt equation, which is this Hamiltonian constraint given previously by Dirac. So this constraint is telling you that there is some Hamiltonian given by your system, that over the wave function of the universe, which gives you all the information that can be in the universe, follow this equation, the Wheeler-DeWitt equation, that h over the psi is equal to 0. This is a very strong condition, and since your system is infinite dimension, the system is not possible to be solved easily. The only way you have to solve this, it looks like the only way, is to keep a homogeneous and isotropic universe that is a free-elemental Rosen-Walker, and then the 3 metric is only described by one parameter, that is the scale factor. This is called the mini subspace. In our case, for example, we are going to add a matter field, some scalar field, which is homogeneous, and this is going to be enough for us. And this is usually done in canonical quantum gravity. We need, from now on, once you know what is canonical quantum gravity, we need something new, that is the third quantization. This is in the 80s, someone thought that there could be some relation between the canonical quantum gravity, like thinking that the universe is completely quantum, and make another step, like from quantum mechanics to quantum field theory. It is like saying that if the universe is described by a wave function, why we cannot do exactly the same with the universe as a whole? So the universe behaves like a particle. So this third quantization is making the universe to evolve like an operator. This wave function make it an operator. So you can build a quantum field theory of universes. Some interaction between universes in the multiverse can be taking place. So this function, for example, can be given by a complex scalar field. And from the vacuum, you can have a pair that is a universe and an anti-universe created by some interaction or anything. We don't know the origin, but these kind of pairs are given in quantum field theory. So we simply replace this scenario in this sense. And then we can analyze what happens to our universe if there is an anti-universe which is entangled, as electron and positron, for example, in a pair creation. We can know what is happening in our universe in this scenario. And for this, what we need is this invariant vacuum. This vacuum, exactly, the initial one is a vacuum that means no time and not space. So as Hawking said in the 80s. So this vacuum of no time and not space is only for, it's just a general picture, but in quantum field theory, it means like the minimum in the minimum level of energy. No? So in the invariant vacuum, we want exactly what having a background, a metric, a general metric that is changing in time. What is not conserved in quantum field theory in curved spacetime is that the number of particles is not something well defined. So in our case, we need a representation of the Hilbert space such that the numbers of particles, the number of universes is conserved. So we need to find a representation where this vacuum, this state, is conserved during the evolution of the universes. So this invariant vacuum is telling you that the number of universes is going to be kept invariant, but you cannot now use the Hamiltonian you had previously because you need to describe the Hamiltonian in a new way. This invariant vacuum, written like this for the universe and the anti-universe, the combination of them, is written like a linear combination of the old state, the diagonal states, the old ones. So this is, all the Wheeler-DeWitt equations are similar to a system which is a harmonic oscillator, a time-dependent harmonic oscillator. So Lewis and Rosenfeld in 69 developed a way to find the invariant vacuum from the Hamiltonian of this type. So we simplify the entanglement entropy of these two pairs by tracing out the degrees of freedom of the other. We find the density matrix knowing this invariant vacuum, and then we reduce the degrees of freedom of one of them. So the von Neumann entropy of this bipartite system is giving you the entanglement entropy of the system. And this entanglement entropy is quite important at the end because it's giving you some physical details. If we have only a system with Friedman-Lemaitre resolution Walker, this scale factor and some phi, which is massless, or the potential is 0 in general, the Wheeler-DeWitt equation is written like this, where this f is a function of just the scale factor, the cosmological constant, whatever you have. So here, this function, all this term here, comparing with the harmonic oscillator, is a frequency. And then you can perform a Fourier transform and see that this psi can be written like this, where A is a wave function. It is the distribution of the modes of the scalar field. In this case, if we want to keep the image that you have a universe and an anti-universe, this psi cannot be anything but something where this A is symmetric around 0. So this is telling you that the energies of one universe and the other is exactly the same. At the end, you get exactly the same energy for both universes, something which we physicists like, this kind of symmetries. And we can calculate with this kind of wave function the entanglement entropy for any model, like that have this kind of Wheeler-DeWitt equations. But we find in just 2 models or 3 models, you prove this, that entanglement entropy at the maximum and the minimum of the evolution of each model, the entanglement entropy diverges. And this is something that was told by Kiefer in the 88 in an article called the wave packets in the multiverse, I think is the name of the article, that at the maximum expansion of the universe became highly quantum. And this is something interesting because this entanglement entropy of the pair is telling you exactly the same, that when the Hubble parameter is 0, you find that the entanglement entropy diverges. So we check that this statement looks true. So we found, not even that the entanglement entropy is imaginary out of the classically allowed regions. So you find the Friedman equations, you know that the universe can be between A minimum and A maximum, and out of this interval, the entanglement entropy is imaginary. So you find a way to find what is the maximum or the minimum of your universes, just looking at the entanglement entropy. And the entanglement entropy was a quantum calculation, a calculation coming from quantum gravity. So this is not a classical calculation. We check, for example, this oscillating universe, the universe that has the shape of the sinus, for example, and we check that in the inflationary point that is in the middle, where the first derivative is not 0, we find that the entanglement entropy does not diverge. And this is a nice point because we see that the entanglement entropy diverges if and only if H is 0, if the Hubble parameter is 0, exactly at maxima and minima, but not in any inflection points. If H is not 0, the entanglement entropy is not divergent. So we find this quite interesting because we can find what is the relation between entanglement entropy and the Hubble parameter. But we studied any other things in the middle of the calculation. We found that for Renyi and Tsallis entropy, they are exactly the same, and the behavior is the same. And we found that the temperature of entanglement, that was something previously given as a measure of quantumness, is not a good measure of quantumness as seen in some exotic singularities model, where some models that have some exotic singularities. The point is that entanglement entropy can be expanded around the maxima and the minima of the models, and we check that we expect to be related with the entropy of a black hole, like 1/h², but it doesn't fit. It fits perfectly like the logarithm of the Hubble parameter. So we found that the entanglement entropy around the maxima and the minima behaves like the Shannon information, like minus logarithm of h. And this -1 is almost perfect. So around the maxima and the minima of the classical evolution of the universes, the entanglement entropy behave like this. And it depends on your initial conditions of the universe to know what is the initial entanglement entropy. And that is something interesting. So some conclusions we get from this is that the entropy of, we find a way to calculate the exact entanglement entropy. We know that the modes are symmetric around 0. And we know that at the maximum and the minima, the points are highly quantum. And that the temperature of entanglement is not a good measurement of the quantumness, that entanglement entropy goes like a Shannon information in the maximum and the minimum. And the perspective of the theory is that we need, of course, some better models like having a massive scalar field, or see what happens with the CMB and the dynamics of the universe in this kind of models. So I'm running out of time, so I think this is enough. So thank you very much. These are the references if you want some.
Okay, thanks, Samuel. Okay, so we can have some questions. So if you have, please. Yeah. Okay, Ian. Yeah, please
Yes.
ask.
So this entropy diverges at the critical point, but I guess it's not physical, right? And it can be regularized.
The dimension of the system is infinite. I mean, when you change the linear, invariant vacuum in terms of the Fock state, I mean, all the dimension of the Fock space is infinite. So if you have a bipartite system, the entanglement entropy, the von Neumann entropy, is goes from 0 to the dimension, to the logarithm of the dimension of the Hilbert space. So it is allowed to be infinite. So it is physical.
I see. Okay, thanks.
Okay, so next, Takahiro Terada. So you.
I had a similar question. So you assumed the mini superspace approximations. I thought the degrees of freedom, number of the degrees of freedom was small, but now you said that there are infinite. Right?
It is due to the formalism of the invariant vacuum. The degrees of freedom of the mini superspace is 2, but the linear combination of the vacuum state with the diagonal state must be infinite. It's an infinite combination of a state. So the dimension of this Hilbert space is infinite.
Thank you.
Okay, thank you. So there's no questions. Okay, thank you again, Samuel.
Okay, thank you very much.
So, yeah, so let's move to the next talk. And next speaker is Andreas Mancheris. We'll talk about cosmological implications of electric vacuum stability. Okay, so are you ready?
Yes, yes. Can you hear me and see me?
Yeah, good. Yeah, please start.
Excellent. Okay, great. So hi, everyone. Thank you very much for having me and for allowing me to present my work. My name is Andreas. I'm a PhD student at Imperial College London, where I work with my supervisor, Arthur Ayanti, on this topic of the electroweak vacuum instability, particularly in this cosmological context. And we're also collaborating with Tommy Markkanen. And in this paper that I quote here, we derived these constraints on the Higgs curvature coupling from inflation. So we adopt this kind of conservative approach where we want to make use of the very essentials, and in our approaches, this is the standard model of particle physics. And this is motivated exactly from the data, from the measurements. So the experimental values that we measure, especially for the masses of the standard model particles, for this particular topic, the heaviest ones, the Higgs boson and the top quark, are the ones of importance. So these measurements may dictate that the standard model on its own can provide a consistent minimal model to describe the early universe, because in principle, it can remain valid all the way to higher energy scales, maybe up to scales where you need to start considering quantum gravity. And this argument comes from the fact that if you have a look here on my left-hand side plot, where I show you the Higgs self-coupling lambda and how it evolves with the energy scale mu. You see that there are no discontinuities, poles, or any fancy behavior. It's just a smooth function, and there's nothing, anything going wrong at these higher energy scales here. So from that point of view, from an internal point of view for the standard model, there are no inconsistencies. It can pretty much be used throughout all these energies range. For most of these, for these curves, you see that lambda also crosses 0. And this is actually the fact that gives you this problem of electroweak metastability. I say for most of them because you see here in these different colors the effects of the uncertainty in the top quark mass measurement. So for some of these, still you never cross 0 and metastability never arises. But for the ones that cross 0, how we can see how metastability actually arises. So here now, if we look at the right-hand side, I have the plot of the Higgs potential versus the Higgs field value. And right here, we have the usual Mexican hat potential. Here we find ourselves into the electroweak vacuum state, where the Higgs has the usual VEV, it couples to the particles, it generates the mass, and this is the usual Higgs mechanism physics that we know in the standard model. But now, if lambda turns negative, we know that the Higgs potential is a lambda filled to the fourth function. And that means that now that lambda switches sign, that you will develop this second deeper minimum here on these higher field values. And that creates this problem of metastability because we're dealing with quantum fields. And for quantum fields, there are always the possibility of quantum tunneling. There's always a non-zero and finite probability. So you're even if you're here safely in the electroweak vacuum state, you can always find yourself decaying to the true vacuum where your Higgs field will have a different VEV, and it will dramatically change your physics. Of course, you can cross over the barrier in a classical way or have a mixture of those two processes. So this is what motivates the study, this metastability. And because we're still finding ourselves to be, through our measurements, right, to be in the electroweak metastable vacuum, that means that if we consider this problem in the cosmological setting throughout our cosmological history, we can establish this very nice link between this particle physics problem and cosmology and constrain our fundamental theories. Okay, so just to be a bit more specific about it, so what if this vacuum decay happens? What does that mean? And that means that at a specific point in space-time, you have this decay taking place. It's a local phenomenon, and then it excites the surrounding space-time around it to also decay. And you have a growing bubble of true vacuum, and it very quickly expands with velocity close to the speed of light. Within the bubble, we don't really know what is going on. For the practical purposes within the standard model, we just assume it to be a singularity. So effectively, you have a spherically symmetric, growing, very, very rapidly growing singularity, and that it devours the universe around it as it grows. So that's a catastrophic event from our point of view, because you won't see it coming once it nucleates, and it will destroy, it will devour the universe as you know it. So from that point of view, it's something hostile towards us. And how you can quantify this and study it, we do it through this expectation value of the number of bubbles of true vacuum that can have nucleated. It is in these curly brackets, this n. And this is nothing more than just a decay rate, the probability for the process to happen per space-time volume, times the space-time volume that you're integrating over. And that, as we said, because we still measure our universe to still reside in this metastable vacuum, that means that it couldn't have been a significant bubble production in the entirety of our past light cone, the entirety of our cosmological history. Because if there were, because they grow so fast, they would already have reached us. So we can safely say that within our observable universe, the probability of having 0 bubbles through vacuum would have been significant enough. And that's why we are now introducing this Poisson probability distribution, because we deal with rare events, and that's where the expectation value of the bubbles comes into play. And from this argument, you get this constraint on this expectation value, which effectively says that you couldn't have exactly significant number of bubble production. The maximum number of the expectation value cannot be more than 1. So even though the decay rate gamma is very low today, so the probability for the lifetime of the vacuum is longer than the age of the universe, so we're not under threat of it in the present day, there could have been significantly higher rates and mechanisms that would have triggered vacuum decay in the early universe. And this is what motivates us to study this phenomenon in the early universe in order to constrain our fundamental theories. And that's why here at the bottom, I give you the integral from before, the expectation value for the bubbles, but now written as you would like it during inflation. So now we're integrating over e-foldings of inflation, which is just a variable that counts how much inflation has taken place, and we can constrain it very easily from CMB measurements. So everything here just has to do with a space-time volume, because that's what it comes into, apart from gamma. And then we only have 2 free parameters in here. One has to do with the total duration of inflation. We just minimally assume that it should last 60 e-foldings, which is the lower bound. But there is a comment on the total duration of inflation. So if you fix this to 60, then there is only one residing free parameter here, which is this non-minimal coupling psi, which comes from gamma. And by imposing this constraint here, you can obtain constraints on this coupling. Okay. So since the seminal work of Coleman, Kaeler, and De Luce in the 70s and 80s, you have there are these very famous solutions, classical solutions to these tunneling processes from false to true vacua called instantons. And specifically in our case, because of the high Hubble scales during inflation, the Coleman De Luce instanton approach is the much simpler Hawking-Moss instanton, which is characterized by an action difference given by this equation here in blue. So this is written as a function of the Ricci scalar, which characterizes space-time curvature, and also is given in terms of the height of the potential barrier. So this is delta V is the value of the potential of the Higgs potential at the top of the barrier minus the value of the Higgs potential at the electroweak at the false vacuum scale. And the reason for this is because the Hawking-Moss instanton, which dominates at this epoch, is a classical process. It takes you over the barrier, and that's why the height of the potential barrier comes into play and nothing else. So by using this Hawking-Moss instanton, you can write your decay rate to look like this now. And you see everything is written in terms of space-time curvature, and this is in fact what is the important thing to consider in this scenario, that the space-time curvature plays a significant role. Already, if you look at the tree-level potential for the Higgs on its own, the curvature effects will enter through this non-minimal coupling. This is exactly what we're trying to constrain, and it does exactly what it says it does. It couples the space-time curvature with the Higgs field. Here you have your usual, of course, quartic part for the potential, the thing that gives you this aspect of metastability to begin with. So if you want to go beyond that and consider extra terms, and you want to have a more state-of-the-art Higgs potential, you can include your loop corrections and your curvature corrections in the sitter at one loop, and you end up with this more complicated expression. Again, here you have non-minimal term, you have your quartic term, you have a term that is generated, it's a gravitational term that radiatively is generated, and you have your loop correction, and this is the loop correction in the standard model, which is a very complicated expression, which we don't have to worry about specifically what it means. We just look that it goes through all the way through all the degrees of freedom of the standard model. So we want to simplify our potential a bit, and we want to get rid of this scale dependence, the renormalization scale dependence in our potential. And this is done via this process called renormalization group improvement, where we choose the scale mu to be a function, we call it here mu star, a function of the Higgs field and the space-time curvature, in such a way as to exactly vanish the loop correction. So if we plug in mu star in here, this should give 0. So by doing this, we obtain this renormalization group improved, effective Higgs potential. Now there's no scale dependence here. We've just subbed in new star here, and we just have to deal with these three terms. And all of this discussion is just to complete this calculation. So we did this because we want to, at the end of the day, we want to calculate the height of the potential barrier. And that's where this RG improved potential comes into place, because this is what is required to go into the gamma decay rate. Then in our case, we're studying this during inflation. So we want to choose the whatever inflationary model we want to consider. And this we do by specifying a potential for the inflaton field that feeds inflation. Then we want to complete the calculation of the bubble integral that I showed you before, and we want to impose this condition on the expectation value. And by doing this, you can constrain the only remaining free parameter in that expression, which is this non-minimal coupling psi. So you obtain a lower bound, which is set at the place of equality, at the place where you have exactly one for the expectation value of the bubbles of true value. And this is exactly what you see here in this plot. You see these lower bounds on Xi versus the top quark mass. And the reason that we have the top quark mass on the x-axis is exactly because of the uncertainty in the mass of the top quark. So here at the center, you have the central value in the top quark mass. And with the three colorful lines, you see the bounds in the three inflationary models that we studied. So quadratic and quartic are self-explanatory, the usual monomial potentials. Here with Starobinsky, we denote this power law Starobinsky model. It's not the full R-squared model. It's just plugging in by hand the exponential potential as a first step. And also you see here, apart from the central line, the 1 and 2 sigma deviation in the top quark mass. So because these are lower bounds, you manage to exclude this area of your parameter space. So this area above is the one allowed. Of course, there is a hard cutoff because of the range of validity of the Hawking-Moss process. It is Xi cannot be more than 1/6. So if it doesn't extend all the way to plus infinity. And also there's one important thing to talk about here at the left. So this vertical black line here denotes the lightest the top quark can be, before which lambda will never turn negative as it runs. So if you remember, going back to that very first slide that I showed you, lambda for some values of the top quark mass wouldn't turn negative throughout. So if lambda never turns negative, your potential never develops a second minimum, and that means you don't have the metastability problem to begin with. So this is a hard cutoff of the plot. There's no way to go beyond that from this kind of studies. This other horizontal line here is a softer cutoff in our plot, and this just depicts the lowest value that the non-minimal coupling can have at the electroweak scale, below which Xi will turn negative as it runs with the energy scale, because Xi is also a running parameter. It depends on the normalization scale. So if it starts from a lower value than this, then as it runs, it will turn negative, and that can potentially destabilize the potential which we saw before. And that means that you have to be a bit more clever about how you're going to be dealing with that. So in this study, because now we're talking about this region here of the parameter space, which is further away than the 5 sigma from the central values, we haven't looked at what this means. So that's why the curves terminate here. Okay, so this is the main plot of the results, but we can be a bit more quantifiable about what this means. So in this plot here, I show you the probability of bubble nucleation on the y-axis. This is just the integrand from before. Versus the e-foldings of inflation, we set 0 at the end of inflation, and growing numbers look towards the earlier times of inflation. And in each of these models, you see these well-defined and localized peaks. that take place towards the end of inflation. And what this means, it means that our bounds that we obtained in the previous plot are reliable enough, because if bubbles form during the last e-folding or so, then because there is a certain amount of de Sitter approximation when calculating the Hawking-Moss bounce action, then that would mean that you would have this unreliability there, because spacetime deviates significantly from de Sitter in the last e-folding. On the other hand, if the bubbles would form predominantly at earlier times, at much larger than the 60 e-foldings that we have assumed, then these early times will dominate your results, and then you wouldn't be able to trust this calculation that only takes into account the last 60 foldings of inflation. So here we just see that you have the bubble nucleation taking place close to the end of inflation, but before the last e-folding, so that's great news. And you see it dropping rapidly for the larger e-foldings. So that means that the early times as well should not really play a role. And with the fainter lines, you also see again the effect of the mass uncertainty in the top quark. But one more thing that we want to talk about is to be a bit more precise about these early times, because in principle, inflation can last for many orders of magnitude longer than the 60 e-foldings. And this is easy to do in this calculation, because we just will split the usual integral that we've been calculating into two. One that ranges from 0 to 60 as the integration limits, and one that ranges from 60 up until whatever high value of duration you want to have. Now you can go at the extreme case, because we've calculated the bounds from before, and you can set the first term that we've been calculating to be exactly at 1. We choose psi to be exactly that. And then for the second term, now the slow roll conditions apply here. And that means that your calculations will be very simplified compared to this calculation here, which is a much more complicated one, both analytically and numerically. Now also the Hawking-Moss bounce action approaches a constant value at these high curvature scales at these early times. So that means also this will come out of the integral. And once this happens, then that means that you can actually calculate this second term analytically, and specifically for monomial inflationary potentials, and also potentials where the Hubble rate approaches a constant, which are the realistic ones, then you get this very nice result, where you see that it's just a function of the total duration of inflation. And what this means is that the only way for the early time contribution to make any significance, to affect the extreme case of one bubble of true vacuum, is only if the duration of inflation is comparable to this number here. And because now this is a constant, as we mentioned, and this a very large number is something like 10 to the 60, much longer than the 60 foldings that we've assumed, we see that it's not a realistic number. So that means that we gain confidence that the early time contribution should not affect these results. But of course, because this is not an infinite number, although it's a very big one, that may hint against models of eternal inflation. But of course, this is nothing rigorous we can say from this here. That might be a hint. Okay, so I think I'll give you the conclusions here, because I think we're running out of time. So we just included this one loop curvature corrections beyond de Sitter into our Higgs potential to obtain this bounce on the non-minimal coupling psi, which we see here in numerical values, just the minimal assumption that inflation lasts 60 e-foldings, and we saw that they are model independent from an inflationary point of view. Also, they don't depend on the total duration of inflation, and you have the expected dependency on the top quark mass. The reason for the model independence on the inflationary model has to do with how you tune, of course, your inflationary models. And I have a next step for Starobinsky inflation, where you consider actually the full R-squared model. But because I'm running out of time, if there are questions, we can go over that. But other than that, thank you very much for your attention, and I'm very happy to take questions.
Okay, thanks, Andreas. So if any questions? If you have, maybe it's time over, but
May I
okay.
ask one quick question?
Okay.
Could you remind us why you do not go beyond the conformal coupling?
I think this is the range of validity for this Hawking-Moss instanton. So if you go beyond that, it breaks down. And I think already before reaching this 1/6, you have then you limit your validity. The Hawking-Moss instanton is valid for values of psi much lower than 1/6. Well, it goes from 0 to 1/6. Yes.
Isn't it possible to go to the Einstein frame and analyze?
Yes, exactly. And this is what if you do this R² model, this is what we're doing now. And then I can show you in this slide. Then if you do your conformal transformation and your field redefinitions, you end up with something like this. And here now you have in the potential, before we only had these terms here in the potential for the quartic and the quadratic. But now you have all these extra terms that come into play exactly because of the conformal transformation and the redefinitions. So this is now in the Einstein frame.
Okay, thank you. So now time is passed. So now I think we have to close this session and thank for all the speakers and the audiences. Okay, see you again in the next plenary session. Goodbye.